Hello, my name is Jesse Park, and today I'm going to be speaking about the parameter optimization of tensegrity structures as a part of the Davami Research Group here in the Department of Mechanical Engineering at the University of Alabama. So to begin, what are tensegrity structures? Well, they can best be described as a network of compressive members held in tension by a network of tensile members known as cables. So this combination of bars and cables allows for a self-stressed equilibrium state that resists external loading, including gravity. This is where we come with the anti-gravity configuration of these elements, presenting unique properties as mechanical metamaterials. Now, what's interesting about tensegrity is that they actually have their origins in as early as 1940s in art, and as well as coming in the 1960s in architecture. So that's why a lot of the current examples you'll see in tensegrity are mainly in bridges and other art designs, but we have applications actually in the engineering industry. So what are these modern applications? Well, due to their lightweight, deployable, and impact-resistant nature, these tensegrities have applications in endless industries, including robotics, material science, and the aerospace industry. Now, we even see this in the figure here with all these examples of the tensegrity robots, where they have been utilized in various projects, even working with NASA. Even here at UA with our Agile Robotics Lab, we see the use of tensegrity in robotics. However, it's also important to note that tensegrity is not limited to only engineering fields, but also has implications in fields such as biochemistry, where we can model cells, the cytoskeleton of cells with tensegrities, as well as even a DNA helix. So with the growth of additive manufacturing, we see an increase in the production of these tensegrity structures through these methods, specifically vat photopolymerization. If you're unfamiliar with this method, this essentially consists of a vat of resin which has a build plate submerged, and then each layer is cured by a UV laser, allowing for the fabrication of these structures. Now, what this vat photopolymerization allows for is essentially higher precision structures of these tensegrities, as well as a higher tunability, allowing us to explore more complex tensegrity structures than previously done by hand. Now, there's currently an issue with this fabrication method, which is that we cannot construct purely tensile members. This has led to the increase in tensegrity-inspired structures, which rely on their certain pre-stressed geometry to achieve this tensegrity behavior, even only being only consisting of struts. Now, this mimics the typical response of tensegrity structures with their bistable behavior. So for our structure in particular, we focused on the Double T3 structure, which can best be described as a right triangular prism, which has been reflected over its top face. Here, the bars are denoted in blue and the cables are denoted in red, so you can understand which members are experiencing tensile and compressive stresses respectively. And so once we have this prism, we mirror it over its top face to get our Double T3 unit cell, and then further expand that to our lattice, which consists of 2 layers of 10 unit cells each. So here you can see the workflow for our total fabrication process. First, we start off with the design, which takes inspiration from previous tensegrities done in other literature. From there, we create the model in SolidWorks, and then we send it to the Form 2 SLA printer for fabrication in that vat photopolymerization as I previously described. And then from there, we wash it in isopropyl alcohol to remove any uncured resin, and then finally cure it to achieve the final material properties that we are looking for to examine. So the objective of our study is to optimize 3 of these key design parameters to maximize specific energy absorption. So the first parameter that's important to note is the pre-stress angle, which is the difference in orientation between the top of the triangular prism and the bottom of the triangular prism that make up the unit cell. The second important aspect to notice is the B to A ratio, which is the diameter of the circles that circumscribe these triangular faces of the bottom and then, once again, the top triangular face respectively. Finally, we sought to examine the bar to cable ratio, which is the thickness of the bars and cables respectively. And this is all done to optimize this equation here at the bottom, which is the specific energy absorption equation, which is essentially just the integral of the force displacement curve divided by the mass of the sample. Now you may be wondering, well, what's the point of all of this? Well, the point is that by maximizing the specific energy absorption, we can see implications for these highly producible structures. So think maybe we have a payload we need to drop without a parachute. Say maybe there's high foliage, we cannot drop it. We need something that can repeatedly take impact, absorb a lot of energy, and is low weight. Think also crash systems. So, currently we have those sandbags that disperse force, but what if we could employ these structures for really any energy absorption applications? So for our compression tests, we use two main methods, one being the quasi-static with the Mark 10, and the other being direct impact with the Hopkinson pressure bar setup. I will go more in depth into those methods now. For the quasi-static setup, we focus on low strain rate compression. Now what this means is that we compress the samples at around 13 millimeters per minute. And if you are unfamiliar with how a quasi-static compression test works, think of your typical hydraulic press where we put the sample at the bottom plate, and then we slowly lower the top plate at a set displacement rate, measuring the reactive force so we can determine the mechanical properties of the structure. For the direct impact setup, we sought to get higher strain rate compression, which results in around 5.5 meters per second, and that the way this REL incorporated direct impact setup works is that we pressurize this tank of air, and then we suddenly release it so that it fires an aluminum striker bar at our sample. From there, we record the force of impact using a load cell, and for tracking the displacement, we use an Amatec Phantom V611 high-speed slow-motion camera to calculate the displacement and align it with the force data. And that was shot at 55,000 frames per second, so by reworking that, we can get all of the necessary data. So here we see the results of varying this pre-stress angle. The original angle we started with was 30 degrees. So from there, what's interesting to notice is that with all the decreases in angles, we see an increase in the bistable behavior of the tensegrity, which is promising because this is the whole point, is that the tensegrities, due to their twisting, exhibit this dual behavior, this dual stable behavior that we're looking for. And so that increases overall. However, the specific energy absorption actually decreased up until 13 degrees, which we initially thought might have been concerning for our results. However, we saw that after that 13-degree point, with decreasing angles, it actually drastically increased up to our optimal angle of 1 degree of pre-stress angle. Now, using this optimal angle of 1 degree, we sought to optimize the B to A ratio, which, as I remind you again, is the diameter of the circumferences that circumscribe the triangular faces. And using that optimal angle of 1 degree, we tested other angles, and we found that actually the original angle of the original ratio of 0.75 was optimal, which matches all the previous literature studies that also used this ratio, which we found our studies also confirm with energy absorption. Now, using this optimal angle and optimal B to A ratio, we finally decided to figure out what the best bar to cable ratio was. Now, starting with our original bar to cable ratio of 1, we already had decent energy absorption. However, we found an optimal result at 0.75 for the ratio. Here you can see how our energy absorption compares to other typical trusses and mechanical metamaterials and various other studies, with our value of 3.25 joules per gram being much higher than others. And even if you look at the pre-optimized lattice, it still performed higher than a lot of these other structures at the given relative density. We also conducted fracture analysis at the using optical microscopy. And what we determined was that the majority of fracture happens at the nodes in a ductile manner with 45-degree fracture faces, signifying buckling, which has been shown in other literature to maximize the strength to weight ratio. So ultimately, what have we found? Well, we found the optimal double T3 lattice parameters for this structure for optimizing energy absorption, which consists of a 1 degree pre-stress angle, as well as a 0.75 B to A ratio and bar to cable ratio. We would like to acknowledge the support from the University of Alabama Analytical Research Center. And are there any questions?
You mentioned that one of your findings is this 0.75 for the BA ratio. I think you probably determined that experimentally. I'm wondering, do you have any intuition why that number? I mean, is there anything you can think of just trying to explain how that came about?
Well, intuitively, not so much, other than the fact that so many other papers have determined that this is the best ratio. So I guess in that aspect, just from the literature review, that's kind of intuitively why we think it would make sense, because since all these other papers are doing extensive studies on this structure, there must be a reason why they're doing this ratio, which is why we saw the optimal results already with this compared to the other parameters.
So when we're talking about this optimal angle of 1 degree, have you attempted at all to take this to an extreme of maybe 0.5 degrees or further? And is that even feasible? Like, it seems like 1 degree is already a somewhat confusing shape.
Yeah, so we already chose 1 degree because that's kind of the furthest we could get, right? At that point, the faces are almost basically aligned. So past that, it would be hard to account for the negligible changes in angle at that point.
So why was the pre-stress angle only lowered, and why weren't angles greater than 30 degrees chosen?
All right, that's an excellent question. So yeah, as you will notice, is we only went down in this pre-stress angle, and the reason for that is because an angle greater than 30 degrees would result in a no longer tensegrity-like structure. So at that point, we would lose the pre-stressed elements if we increase greater than 30 degrees.
So since it's physically not possible to fabricate purely tensile elements, how do you ensure that the tensile members only experience that tension?
Yeah, so as I mentioned with the tensegrity inspired structures, that previous studies have been done to kind of optimize these 3D printed structures so that even though they're only consisting of struts, they can ensure that these tensile members are only experiencing tensile forces, and same with compressive members when they're in that pre-stress configuration state.